know that boiling point is a particular temperature at which a liquid starts boiling. And the condition is when the external pressure just equal to the saturated vapor pressure above the liquid. So if we take a solution here in a container, and if we consider at a particular temperature there is a vapor pressure that is P1 for dilute solution having non-volatile and non-electrolyte solute. This pressure, when equal to the 1 atmospheric pressure, 1 atmospheric pressure is the external pressure, then this solution starts boiling. We can easily understand this picture with the help of a graph. Vapor pressure versus temperature graph. For liquid, this vapor pressure versus temperature graph is this curved line. AB curved line shows the vapor pressure curve for pure solvent, and CD curve shows the vapor pressure curve for dilute solution. Here we consider the dilute solution made of volatile solvent and non-volatile, non-electrolyte solute. And AB curve that is due to the pure solvent. As we know, at a particular temperature, always vapor pressure of pure liquid is greater than the dilute solution having non-volatile and non-electrolyte solute. We obtain this relation from Raoult's law of relative lowering of vapor pressure. Relative lowering of vapor pressure we have studied earlier, that delta P by T1 naught, that is equals to x2. Now if we apply the concept of lowering of vapor pressure here at a particular temperature, say this is a particular temperature T, at temperature T the point E represent the vapor pressure of pure solvent P1 naught, and point F, from point F if we draw a perpendicular onto the y-axis, that is vapor pressure axis, we have the vapor pressure value P1. We know at a definite temperature always the vapor pressure above the pure solvent is always greater than that of the dilute solution having non-volatile and non-electrolyte solute. So P1 naught is greater than P1. We know this is the experimental verification which was introduced by Raoult. Now, if I consider that this is the 1 atmospheric pressure, if we consider that this value of pressure that is on y-axis, this point have the value 1 atmosphere, and according to the definition of boiling point of a pure liquid, if the vapor pressure, that is saturated vapor pressure of the pure solvent just equals to the atmospheric pressure, then only that pure liquid starts boiling. That is the criterion for boiling point. So at this point, when we draw a line, parallel line with x-axis from one atmospheric pressure, it will cut AB curve at a point X. Suppose this point gives us the value of vapor pressure of pure solvent is now 1 atmosphere, which is equal to the P1 naught by rotation, and here the corresponding temperature, that means if we draw a perpendicular to x-axis from the point X, that will give us the idea about the boiling point of the pure solvent. At this boiling point, if we observe from graph that it cuts CD axis, it cuts CD curve at point Y, and from Y if we draw a perpendicular onto the vapor pressure axis, you will see that its pressure value is not equal to 1 atmospheric pressure. So this pressure is less than 1 atmospheric pressure. So at this point the solution will not boil. So this temperature TB is the boiling point of pure solvent. So from graph, if we consider that if we extrapolate this straight line from 1 atmospheric point, it will cut CD curve at a point Z, and from Z if we draw a perpendicular on temperature axis, that will give you TB prime. This temperature TB prime is now the boiling point of dilute solution. So this graph, vapor pressure versus temperature graph, gives us clue that always boiling point of dilute solution having non-volatile and non-electrolyte solute So from here we will see that this graph, vapor pressure versus temperature graph, gives us clue that boiling point of dilute solution is elevated. Here TB prime is greater than TB. TB prime is greater than TB. TB prime is the value of boiling point of dilute solution having non-volatile and non-electrolyte solute, and TB is the boiling point of pure solvent. So from graph it is clear that TB prime is greater than TB. So elevation of boiling point. So elevation of boiling point will be TB prime minus TB, that is delta TB. Again, Raoult introduced a statement regarding the elevation of boiling point, which is colligative property, and suggested that this elevation of boiling point of very dilute solution containing non-volatile and non-electrolyte solute is directly proportional to the molar concentration of the solution. So molar concentration of the solution is the main concentration term used here for dilute solution. Molar concentration. Molar concentration, we know that is molality represented by small m, which is equals to the number of moles of solute present per kg of solvent. So this is N2 into 1000 by W1. Its unit is mole per kg. Mole per kg, that is molality. According to Raoult's statement of elevation of boiling point, Raoult's statement of elevation of boiling point. What is the statement? The statement is the elevation of boiling point, of very dilute solution, containing non-volatile and non-electrolyte solute is directly proportional to the molar concentration of the dilute solution. So this is the statement, and from this graph it is very clear to us that as we add non-volatile and non-electrolyte solute, boiling point increases. The physical phenomenon of this type of rise of boiling point can be illustrated easily. If we closely think that due to the addition of non-volatile and non-electrolyte solute, if we compare these two different solutions, one is pure solvent and another is dilute solution containing non-volatile, non-electrolyte solute. Here we take dilute solution containing non-volatile and non-electrolyte solute. That means at the surface of the solution they are also available non-volatile and non-electrolyte solute, and here only solvent molecules are there. So obviously here accumulation of vapors will more than this, and that's why vapor pressure at a particular temperature, suppose P1 naught, and here it is P1. Okay, so this P1 naught is always greater than P1, we know from our statement. As the value is little more than the dilute solution side, so obviously if we increase temperature here, more and more molecules now will participate to escape the liquid state and enters into the vapor phase. So it will quickly reach the external pressure 1 atmosphere. We will consider that the external pressure is 1 atmosphere. So the value of P1 has less to become the value of pressure, vapor pressure, saturated vapor pressure above the dilute solution will take more time. That means at the same time its boiling point will rise. It will be TB prime and it will be TB. Suppose its value is 246 torr initially, and its value is 226 torr. So 246 torr to 760 torr, this difference requires less energy, and here 760 torr and here 226 torr requires more energy, and that's why boiling point of dilute solution is greater than the boiling point of the pure solvent. This is the main fact, and on the basis of that we can easily explain the elevation of boiling point of dilute solution having non-volatile and non-electrolyte solute. The statement is very clear to us that there is a quantitative relation between the molar concentration and the elevation of boiling point. The mathematical expression is delta TB is proportional to molar concentration. So you can write delta TB is equal to Kb into N. Now here Kb is the proportionality constant, but it is known as evoluoscopic constant. Evoluoscopic constant. Evoluoscopic constant or molar elevation of boiling point constant. Another name is molar elevation of boiling point constant. You can define Kb. What is Kb? Kb can be defined as delta Tb by N. So if we consider M equals to 1, if we consider M equals to 1, then Kb becomes delta Tb. Delta Tb. So we can define Kb, that is the evoluoscopic constant of solvent. That is easily we can define it. The elevation of boiling point of a very dilute solution of 1 molar concentration is called the molar elevation of boiling point constant or evoluoscopic constant. Kb. This is of course is the property of solvent. This is of course the property of solvent. Kb is the property of solvent. And it is RTB square by 1000 LV. Kb is related to RTB square by 1000 LV. R is equal to universal gas constant, you know. And Tb is the boiling point of pure liquid, and LV is the latent heat of vaporization. Latent heat of vaporization of solvent. As these are related to solvent, we can say that the value of Kb depends on the nature of solvent. So if you change solvent, Kb value will also change. Interesting point is that the unit of Kb that is equals to Kelvin kg per mole. From this relation, delta Tb, that is the difference in temperature in Kelvin scale, and molarity is the mole per kg. Its unit is mole per kg. So obviously the value, the unit will be Kelvin kg per mole. Another important thing is how to measure the elevation of boiling point. That is measured with the help of a device. Here delta Tb equals to Kb into molar concentration. This is the mathematical expression of Raoult's statement related to elevation of boiling point, and the unit of Kb and the definition of Kb we also studied here. And here also we mentioned the relation of Kb with the property of solvent at T square by 1000 Kelvin. If we want to know from where this relation is deduced, for that we have to consider a thermodynamic criteria. Thermodynamically, we can prove that delta Kv equals to Kv and F. That means the statement of Raoult's law can be proved with the help of thermodynamic study. So this is related to elevation of boiling point.